CH6502 Unit 2. Welcome student. We are going to discuss regarding nicotine alkaloid. Previously we have discussed regarding conine. This time we are going to discuss regarding nicotine alkaloid. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Let's begin with the introduction. Well, as you know, nicotine is the best non-alkaloid found in Nicotina species. When I say Nicotina species, tobacco is its commercial source, but it also occurs in several flowering plants like Sedum X-ray and Vascula cryptogam, that is Pteridophyta, Equisetum, Arvense L, and Lycopodium claventum L. These plants will going to show a nicotine alkaloid specifically. Though nicotine is distributed throughout the plant, the concentration in leaves is much higher, and it is highly toxic and increases blood pressure due to contraction of blood vessel. The physical property of nicotine. Nicotine is a colorless hygroscopic liquid having boiling point 247 degrees centigrade, which is mixable with water. Means it has some sort of polarity in its structure. That water solubility indicates that one as well. The natural nicotine is levorotatory, but its salts are dextrorotatory as well. Physiologically, nicotine minus nicotine is twice as active as plus nicotine. Molar formula of nicotine was determined to be C10H14N2 and the double bond equivalence is 5. The nature of both the nitrogen atoms was confirmed to be tertiary because nicotine formed a diquaternary salt, that is dimethioiodide, with 2 mole of methyl iodide. It also forms 2 isomeric monomethanoids when treated with 1 molar equivalent of methyl iodide. The reaction is given as C10H14N2, that is the molecular formula of nicotine treated with 2 mole of methyl iodide. It will going to give us dimethiodide of nicotine. Oxidation of nicotine with chromic acid gives pyridine 3-carboxylic acid, that is also known as nicotinic acid, which confirms the presence of pyridine ring in nicotine. That means nicotine have pyridine nucleus in its skeleton. Thus, nicotine can be regarded as a pyridine derivative with side chain C5H10N at carbon 3. Here you can see that this is nicotine. On oxidation will going to give us nicotinic acid, so that indicate that it has a pyridine nucleus with a side chain at carbon. This is number 1, 2 and 3. At 3 number we have a branch C5H10N. Pyridine ring account for 4 dBe, that is double bond equivalence. So side chain in nicotine must account for 1 dBe, that is double bond equivalence. Reduction of nicotine with sodium in alcohol yields a hexahydroderivative having molecular formula C10H20N2, and further reduction is quite difficult. The conversion of pyridine to piperidine can account for this reaction. thus confirming the saturated nature of side chain in nicotine, and therefore it must be cyclic in arrangement. Initially, nicotine was believed to be piperidine pyridine, but was proved incorrect. Heating nicotine with hydroiodic acid at 150 degrees centigrade gave methyl iodide, confirming the presence of N-methyl group in it. Moreover, oxidation of nicotine with a mild oxidant like silver oxide yielded nicotine, that is having molecular formula C10H10N2. These reactions ruled out the presence of piperidine ring in nicotine. That means the nicotine have pyridine ring skeleton or nucleus, not piperidine nucleus in its structural arrangement. You can see in these reactions, nicotine treating with hydroiodic acid at 150 degrees centigrade temperature will going to get this, and nicotine treating with silver iodide we can get nicotine, and that indicates that nicotine has pyridine kind of nucleus in it, not piperidine. When nicotine is treated with zinc chloride in hydrochloric acid, it forms an adduct named nicotine zinc chloride, which on distillation with soda lime decomposes to give pyridine, pyrrole and methylamine. This is nicotine zinc chloride, that is a treatment of nicotine with zinc chloride in hydrochloric acid. It's going to form this adduct. The name of adduct is nicotine zinc chloride, and on treatment with soda lime or on distillation with soda lime, it decomposes to pyridine, pyrrole and methylamine. The formation of pyrrole confirms the presence of a 5-membered N-containing heterocyclic ring pyrrolidine in nicotine structure. There are only two positions through which pyrrolidine ring may be attached to this pyridine. Of the two probable structure 1 and 2, nicotine was found to have structure 1. So here you can see that is a 5-membered ring structure, that is the heterocyclic ring pyrrolidine, and with that we're going to have this attachment at carbon number 3, and this structure 1 is considered to be the structure of nicotine. First evidence for the above structural assessment was provided by Painter in 1893. He studied the reaction of nicotine with bromine in presence of hydrobromic acid and obtained a compound having molecular formula C10H8Br2N2O2 named dibromoticonine, which decomposed on heating with barium hydroxide to give nicotinic acid, malonic acid and methylamine. These products can only be explained if nicotine has carbon skeleton like we have seen in previous slide, that is of structure 1. You can see the reaction over here. So if decomposition take place over here, here 3 portion would be there. So treating with bromine in presence of hydrobromic acid, we're going to get dibromoticonine, and that is treated with barium hydroxide. We're going to get nicotinic acid, that is one part, malonic acid, that is other part, and methylamine. So this portion is going to be methylamine, this one. This portion is going to be your malonic acid, and this portion is going to form your nicotinic acid. On treatment with bromine in presence of hydrobromic acid, it's going to give us dibromo ticonic, which treated with barium hydroxide will going to give you nicotinic acid, malonic acid and methylamine, and this product can be obtained only if we consider this structure number 1 for nicotine. So this is the confirmation of structure 1 for nicotine. The structure of dibromoticonic was established in 1973 by Quinn et al. This is the structure of that one, and this bromo derivative of nicotine is going to be obtained. Direct evidence for the presence of pyrrolidine ring and its linkage to pyridine nucleus in nicotine was given by Karev in 1925. Oxidation of nicotine isomethionide with potassium ferricyanide gave nicotine, which on further oxidation with chromic acid produced L minus hygrinic acid. This is the structure for that, nicotine isomethionide, and on treatment with K3FeCN6 we are going to get this intermediate, which further treated with chromic acid we are going to get L hygrinic acid, L minus hygrinic acid. The structure of nicotine was fully confirmed by the synthesis of plus minus nicotine, which was resolved with plus tartaric acid, and minus nicotine was found identical with natural nicotine. Now further we can establish the structural elucidation by the synthesis. Spath and Candia synthesis 1928 is given over here. Ethyl nicotinate, well treated with electrolytic reduction. On electrolytic reduction, it will going to gives us from dione the monocarbonyl compound, which further treated with dimethyl sulfate gives N-methyl 2-pyrrolidone, and that N-methyl 2-pyrrolidone will converted into ethyl nicotinate, which treated with this N-methyl pyrrolidone in presence of sodium ethoxide, and it will going to gives us this intermediate, which further treating acid hydrolysis at 130 degree centigrade will going to get beta ketonic acid, that on decarboxylation will going to gives us this intermediate, which on zinc treating with zinc dust in presence of sodium hydroxide and ethanol reduction take place, and will going to get this this derivative further treated with hydroiodic acid at 100 degree centigrade temperature. We are going to get this ionic derivative, which further treated with NaOH gives nicotine. Craig synthesis. Nicotinonitrile, that is further that is treated with this ether bromo derivative, or we can say Grignard kind of reagent. In presence of H2O, we are going to get 3-ethoxypropyl ketone, which further treated with NH2OH gives oxime. Oxime on treating with zinc acetyl alcohol will going to get this derivative amine, primary amine, which further treated with hydrobromic acid at 150 degree centigrade. The lone pair of electrons shifted to this side, and this part get brominated, so we're going to get this bromo derivative. On losing one proton and bromine, we're going to get nicotine, and treating with methyl iodide followed by base hydrolysis, that is NaOH, we're going to get nicotine. So this is Craig synthesis. Thank you for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge.